Hey everybody, this is Gabriel Cardona, developer evangelist at Ava Labs, and I'm happy to be joined by Stephen Butoff and Patrick O'Grady from the Ava Labs engineering team. This is the bi-weekly developer community call where we get a chance for developers in the ecosystem to come up to speed with the latest and greatest in the Avalanche engineering ecosystem, and then actually interface with our engineers and ask them questions. So today we have a very exciting topics. We are going to be talking about the new Cortina release. We're going to be talking about the HyperSDK update recently. We're also going to have one of our amazing engineers from the Developer Relations Squad come on to talk about some DevContainer integration with the Precompile-EVM. And then we are also going to be introducing a new teammate as well as Q&A. So with that being said, I am now going to pass the mic over to Pog. There you go, gentlemen.
Thanks, Gabriel. Good to see you again, Steve.
Yeah. We're down one man today, but we'll have to make do without Aaron.
Let me see. I got the latest release up here. Yeah, so we got a lot going on today with the releases, and then there's also another release that we plan to drop today or tomorrow. And we'll go through a little bit of a preview there, I think, too. But first up, let's recap. The Cortina 7 release.
Yeah, so I think we might have hinted at this on the last call that this was upcoming, but Cortina 7 ended up completely revamping how we are managing the validator weight and public key diffs on the P chain. So what this concretely means is that rather than having this mechanism called a linked DB for managing the diffs at every height of a block that we can iterate retrospectively to calculate the validator set at a specific P chain height, all of the diffs are handled in a flat database. So this is a pretty low level database change, but concretely what it lets us do is perform really efficient range queries over the data. This would have been the original design, but at the time we were looking into migrating away from these backend databases like LevelDB or Pebble, which may not support range queries. So we had to have a little bit of a hack in the platform VM to basically enable these iterations. But at this point, we've pretty well committed to using a database with range query support for a number of performance reasons, whether it's state sync in the MerkleDB or things like this. So because of just the vast performance improvement of database range queries, we ended up reincorporating this back into the platform VM. And we end up seeing, I think in the benchmark that we wrote, it was, what was the performance improvement? It was like a 60x.
Yeah, I mean, it ranged based on the benchmarks that you were running. Let me pull up the PR.
Yeah, I think that the unit test benchmark was about a 15x speed up, but if you actually try to generate on mainnet data, it was actually closer to like a 60x speed up. So it's a massive speed up here, which is super useful for warp. This is something that gets hit on the warp path. So making this as fast as possible and as efficient as possible ends up directly correlating to cheaper warp transactions. So that's explicitly why we've been kind of working on this path. We'll have some more additional changes in this area, specifically around some locking changes to enable more concurrent accesses and improved caching. But this is kind of the beefy meat of the PR that got into this last release. So I think that there was a regression that was observed in one case on subnets. So we are releasing a 1.10.8 that'll be coming out hopefully today to address that. So you can see here specifically this fixed subnet validator set public key initialization PR. The bug was essentially that we were assuming an invariant between that the subnet validator set was always a subset of the primary network validator set, which is the case typically. But in this case, we were using a subnet validator set at a different height than the primary network validator set, which means that subset relationship is no longer the case. So it's a pretty easy change. But yeah, so we'll be pushing out 110.8 to.
And then you may say, well, why didn't you have tests for this? Well, we did.
we did have tests. So yeah, unfortunately, we basically wrote these like tests to generate a bunch of like random states, and unfortunately, we ended up accidentally having it so that the test only started from the same origin point and iterated back to those random points, rather than starting at every individual time and iterating back. So we had a minor bug in our test that should have caught this before it went out. But anyways,
that's why we need test roll for the test, right? Eventually,
yeah. So, but anyways, yeah. So 110.8 should be coming out with that. There were a couple other pretty cool things in 110.7, I think. So one of the things I want to shout out is the change of the network allowing of private IPs. So generally, we have allowed by default connecting to private IPs because people running local networks will oftentimes have, say, a bunch of nodes running localhost or a bunch of nodes running in like a local VPN or whatever, VPC. And so we've generally enabled that by default, but we did change that so that it is now explicitly disabled for Fuji and mainnet. So that should prevent any kind of like spurious connections to be made on your local network, which for very high security environments, some people will like alert on that because it acts very unusually. It isn't necessarily a security issue because the connections are fully maintained by AvalancheGo and the data that is sent is maintained by AvalancheGo. So there's not any like probing or anything that could be done, but it's just a very weird mechanism that caused some alerts in some of the more security conscious node providers. So good on them for digging into that. And yeah, we'll change that. We changed that default going forward. Yeah, I think that those were the two major things. There were also a couple of fixes on the MerkleDB syncing and also the C-chain tracer fixes from upstream. But yeah, I think those are the main things I wanted to point out for 110.7.
Yeah, the MerkleDB changes in particular were super nice because I guess like we have this really awesome cycle going on right now where like as I push the HyperSDK harder, it tends to push the MerkleDB and the sync package harder, which is going to really help out when we start to integrate that into the X and P chains soon. And so I think that that's been a really productive relationship so far. And in this case, we found a number of different issues. One actually was found by Dan on his own. Another one was found through like the end-to-end CI on the HyperSDK, which turns out to be a pretty good stress test of this whole thing. So we're still trying to find the right way to like kind of incorporate those together because it'd be really nice to be able to run it on some of these CI tasks for the MerkleDB, but we don't want to like have all these dependencies all over the place. But nonetheless, it's good to see that make some more progress too. And then the other thing we didn't note here, which is going to be important for the release going out today or tomorrow, is that we put in backwards compatibility for the database format on the P chain that we're migrating to in 110.8, which is the last of the series of migrations that we had talked about doing for performance. And so this will mean that everything now on the primary network will be height indexed, which is, you may say, well, like, what's height indexing? Doesn't that make sense that you should be able to look up the height of accepted blocks on the VM? Well, no, it has not actually been the case that you've been able to do that. But starting with the next release, that will be the case. And so, I think one idea that's particularly interesting there is the bootstrap fetch optimizations we've been talking about, which is right now when we bootstrap and fetch blocks, we go from the tip and then just start walking backwards until we get back to Genesis. And because we don't have any notion of like heights or like what things are or any ability to fetch by height, it's just slow serial process as we wait for blocks to come back. And a lot of people that are doing like a full archival sync have complained that, like, it's kind of pretty slow on the fetch side, like anything, and execution, but mostly the fetch is the one that's just seems like, why is it taking so long? And so what we'll be able to do is start to actually do concurrent chunk fetching of over ranges of blocks, which should make things dramatically faster. Which is going to be great, especially when we enable Z standard compression on top of that instead of using gzip. We should see some really nice gains.
Yeah, we should really move away from gzip. There's really no reason that we haven't at this point, I think.
Yeah, for some context there, that's been something that gzip was originally added to lower the network usage, but through a number of different benchmarks, we found Z standard, which is no surprise, is dramatically faster than gzip. And so we incorporated that, and it actually is just as efficient, which is pretty much makes it a win-win here. So yeah, we've been testing that in a number of other places, and it's basically been active on the network for some time, but no one's really using it. So that'll be something that we'll definitely play around with pretty soon.
Yeah, to clarify, the node already supports Z standard compression. It's just that the default compression is gzip. So essentially, this would just be changing a default flag. I think that we added support for ZSTD in 110.0, but
Before.
not for. It was. I believe it was added in 110.0, but it was added to the Fuji. It was added to Fuji in 110.1. So the 110.0 pre-release for Fuji didn't have it, but mainnet did. So 110.0 is deprecated for Fuji at this point anyways, because the beacons changed. But anyway, it should be fully supported by the network, everyone on the network. So we could change the default at any time if we wanted to.
The other topic I wanted to bring up, because it's so meaningful for subnet operators, is related to a new sync mode that we're introducing in 110.8 called partial sync mode. So this one is pretty cool, I think, actually, and for people that are actually running subnet APIs, will dramatically reduce the cost of doing so. Do you remember what PR it is? It's kind of far back, right?
I would just look at the dev. Yeah.
Oh, oops. Yeah, I'll go to dev. While I pull that up, you want to maybe introduce?
It's 1769. Yeah. So essentially, what this does is it notices that subnets do not necessarily require the entire primary network to fully sync and fully verify their subnet. So for non-validators, this provides the option to only sync the P chain on the primary network, which can allow subnet non-validators to sync just the P chain and just the subnet, which is going to be super useful for subnet API providers. So essentially, rather than a subnet API provider needing to fully sync, say, the C chain, the X chain, the P chain, and their subnet, and then provide queries on the subnet data, this lets you just sync the P chain and the subnet, which removing the C chain from this flow is a massive boost, especially for smaller subnets that might not have a massive database size. For some subnets, I think DFK has a particularly large state, might not see a huge performance boost out of this, but you will still see a performance boost. But for subnets with a smaller state, this could be a massive speed up.
Not only speed up in terms of initially bootstrapping, but also the amount of data you're actually storing on disk, which for like a small subnet that has like a couple thousand blocks, right? Like the backing of that couldn't exceed a gigabyte, maybe. So like you basically now no longer need to store like hundreds of gigabytes of C chain data.
It'll also substantially reduce the disk growth. So if you state sync the primary network, the disk is probably not going to be that big, maybe like 80 gigabytes or something. But as time goes on, it rapidly increases the disk size. And the reason for that is because the C chain still uses a hash-based Merkle tree index, which doesn't easily enable online pruning. But if you're not using the C chain, not syncing the C chain, you don't have that problem. And the P chain and X chain do not use a hash-based Merkle tree store. So their disk size does not grow as time goes on. And so you'll see basically a substantial reduction in your disk usage, both in the initial sync and over time. So yeah.
And so you may say, well, this seems like great. Why isn't it always the case? Well, so there is one thing that you can't verify, right? So if you only are syncing the P chain, you can't verify imports to the P chain. So for people that aren't familiar, on the primary network with the C, X, and P chain, we have atomic transfers between the two, we call them. They're not really atomic, which is funny. They're kind of async, but they're called atomic. But long story short, like you can take funds from one chain, export it to atomic memory, and then import it from atomic memory on another chain. But to actually validate that import, you need to have been syncing the other chains to know that it was a valid export to begin with. Well, by only syncing the P chain, you can no longer verify that. So you are trusting the consensus of the primary network to verify that. So like all the validators that do have the full state to verify that, and then are just taking advantage of the consensus there and saying, okay, I'm just going to run consensus on this P chain block. Great, everyone's accepted it. There's an import here. I can't say for sure that import is correct, but the network says it is. So that's good enough for me. So this is not some sort of like replacement for a full setup, but it is a interesting trade-off for people that maybe aren't validators and don't need to perform or aren't interested in performing that particular integrity check.
Yeah, it's essentially if you go to like other blockchains, it's very much like a light client, except you have the full state of the P chain. So like that's kind of the assumptions or like the security assumptions here, because of the import TX. But yeah, so that'll be super cool.
Yeah, so this is the feature I'm definitely most excited about, but there's some nice unlocks in this thing with the DB migration to get us to this world where we have height indexable chains. So yeah, I think that's probably it for the AvalancheGo side of things. Is that right?
Yeah, no, I think those are the major things coming down the pipe right now.
All right, so let's now cut over to some more of our other research into what's going on in the HyperSDK, which, again, to remind people, right, like although it is a separate repository, there is a ton of stuff that we're working on here that goes right back into AvalancheGo. And so there's a few here that I want to first call out. So the first thing, I'm actually going to skip this one. Big change that got merged in the last few days was continuous block production. So this we could talk about for a long time because there are a lot of trade-offs here on like what we're actually looking into. But the long story short of this one, I'm just going to write this down, is that on all of the virtual machines on Avalanche, everything block production is what we call quiescent. So if there's no transactions to produce or add or introduce, like we don't add a block or in the past create a vertex in the DAG. So you may say, well, okay, that makes sense, right? Like if your consensus engine can support not having to like keep things up to date with slots and epochs, everything like that, we should just not produce blocks. And so for like subnets that are small or growing, you don't have a lot of traffic, right? Like that can mean that there's substantially less block data around, and like you don't have to compute as many Merkle roots, and like it's easier to do a full sync, right? Because you don't have all these extra blocks you need to produce. However, it is not without compromise. So especially with the introduction of Snowman++, we have this notion of a validity window. So I'm actually going to pull up. I wrote up a number of the different trade-offs here. So first off, I wrote a thread about this too. if you guys want to read it on Twitter. But the notion here is Snowman++, or what we call the Proposer VM, has a 30-second protected window, it's called. And so for every 5 seconds, one more proposer is added to be allowed to produce at that time. But once 30 seconds passes, we fall back to Snowman. All to all, or anyone can produce consensus, produce blocks and add them to consensus. Now, this can lead to like rejections, but if you have like, very few transactions and very few blocks, it usually doesn't lead to anything, because you can just submit it. Whoever issued the transaction submits a block, and then there's not a lot of rejections. But the major savings here is in the AWM diff lookback worst case. So in every proposer VM block, there's a reference to the p-chain height that's being used to actually verify that. And that is just picked. There's a formula. We kind of talked about this a few dev community calls ago about exactly how that number is picked. You don't want to pick it so close to tip that some people may not have seen it yet. Well, they'll reject the block, but you also don't want to pick it too far back, because then they have to basically generate diffs to understand what the validator set is, or set was at the time that the p-chain height was referenced. So you kind of want this sweet spot. So imagine the previous block is produced that way, and then no block is produced for another 3 hours. Well, when the next block is produced on the subnet, it can then pick a p-chain height, the producer, anywhere from the last p-chain height that was referenced in the last block to the current p-chain height. And if someone was to be, tricky, they could pick a p-chain height that's very far back, so that when everyone's, like, let's say some block has a bunch of warp messages in it, gets verified, that you have to do a lot more diffs than you need to. And so the more diffs you have to do, the longer it takes, the worse it can be for the chain. And so if you want to avoid this problem entirely, you can produce a block always, even if it's empty. And then as long as there's like one honest producer on a regular cadence, they'll pick a p-chain height close to the tip, and you completely get away from this problem entirely. The last one is actually two more. The second one the third one I care about a lot is actually HyperSDK specific, which is, we have these nonceless transactions, and which is super convenient. And the way that they work is you basically specify a time that they're valid to. And then when you're syncing a chain, or like syncing to a HyperVM chain, you end up having to observe that validity window of seconds before you're willing to go healthy. And so in the case of, the default case, I think, is 60 seconds. So after you've already synced state, you basically have to sit there and wait for 60 seconds of blocks to make sure that you've seen the entire window and can actually ensure that no repeat transactions are included in blocks. Well, if you don't have continuous block production and you just sync a node, you may end up being stuck in this like waiting for readiness state until another block is produced, which from like a DevOps and infrastructure UX is pretty terrible, because like your auto deployer system now is like completely broken, right? And so in the CIs, before I made this change, I was sending like kind of junk transactions every so many seconds to like prevent this from happening. And, when you start to do stuff like that, you realize maybe there's a different way we can approach this problem. But the last one I think is actually more interesting for developers, which is this now provides a really nice framework for implementing chain and validator-driven transactions. So some people have reached out saying, hey, I have all this stuff happening on the HyperSDK, but there are like some number of things I'd like to do on a regular cadence to, update state that shouldn't be driven by user transactions. Well, there hasn't really been a framework for that, because when you issued a transaction, or like if you wanted to produce a block, there was no control to say like, oh, there's this empty block with extra things in it that should be valid. So instead, with this framework, we can now add the ability to like post block execution, do some extra stuff. And then there's rules inside of here to regulate how often those can happen, which is pretty nice. So this was a big thing that we've been talking about for a while. There's also some nice consensus improvements that actually come with this, but we'll wait to go into those until those are actually enabled. But yeah, this was a big thing that we were pursuing. I'm not sure, Stephen, if you have anything you want to add to there. I know you we talked a lot about this one.
No, yeah, I think that it's a really nice improvement. If only to keep like your chain time up to date, it's really nice. We have a number of things in like the P chain to kind of support this. So like as an example, say a validator, it's time for them to unstake, like the chain will need to like kind of kick them off. And so they kind of have these like chain implemented transactions. So there are definitely a bunch of use cases for those things. I think that the diffing is probably actually less of a critical update now because of the performance of the validator diffs actually being pretty fast at this point. But yeah, no, I think that this is nice improvement for sure. Yeah.
And now the other thing that I've been spending my time on, which I think is way crazier.
We're about to go down the rabbit hole, absolute rabbit hole.
Is concurrent batch verification of ED25519 signatures. So this one is this actually, funny enough, started when I was, there's two big bottlenecks on the HyperSDK right now without programs. Those are signature verification and tri-E modification, particularly hashing. If we had superconductors to solve those problems, like we'd be good, right? We don't, and so there's some new like instructions in Intel or x86 processors called the AVX instruction set that in certain cases can let you like pass a bunch of hashes to the CPU to do all at once, and can be much faster than just doing them iteratively or even like across threads as you might do in like a normal programming language. And so we're looking at ways to do that, or like using some sort of cool like FPGA or like GPU sort of stuff to try and like speed up the hash throughput. We're pretty early there, admittedly, so you're not going to see many references to it, but more so thinking about the capability. And one night, late at night, I was working on like thinking about that, and I was like, I wonder, this sounds kind of crazy, but like I wonder if there's like similar instructions for batch verification of signatures too. And short story, no, there aren't, but there are other things, which is you can actually batch the verification of the signatures of some types of signature types. In this case, we're talking about Edwards. There's some other stuff you can do with Schnorr and things too, but in this case, this particular scheme, and it turns out that people like went through this period of discovery already like a few years ago, which is the best scenario, right? Because then there's like, oh, you just turns out you weren't searching for the right repository, and so there's some great articles about all of this stuff and what should be required to make it possible. But really, the important thing is that the signature must be cofactored for this to work correctly. And I'm not going to go into that conversation because then there's a lot we'll have to cover. But long story short, what this means is that the Golang standard library, which includes ED25519 signature verification, that takes about 45,000 nanoseconds to perform a single signature verification with no option to do any batch verification. And that signature is not cofactored, so cofactorless. If we switch to batch verification, there's this great library actually that the Cosmos ecosystem maintains called ED25519-VOI. We can reduce the time per signature verification from 45,000 nanoseconds to like 9,000 nanoseconds, which is like huge, right? With no downside in terms of like what security brings to the chain or anything of that nature. So I wrote all these benchmarks to see it in practice, and it does work. And the cool thing as well is that it also is that all that verification is purely single core. So I've been spending time introducing this because if we can reduce the signature verification, load on the HyperSDK, that just improves the ability for us to, process more transactions. It also makes block verification more DOS resistant because, if you're doing operations on the network and are forced to do them, and someone sends you like something that's a malicious block and you spend more time on it than you need to, not great for your node. So this was a really cool thing I discovered. Nothing of my own volition in terms of driving to a useful solution, but sometimes that's how programming works, and that's what the really cool aspects of the open source ecosystem that crypto really pushed are.
And for a little bit more context as well, so like SecP 255 or SecP 256K1, that takes around 100,000 nanoseconds to recover the public key, which you then typically need to then hash to verify against an address. So that's what a lot of chains currently use. So like Bitcoin heavily uses SecP, Ethereum, at least in the execution layer, currently uses SecP for all their addresses. We use SecP for a number of our locations, both P, X, and C chains. So going from 100,000 to like 9,000 is a pretty solid improvement for what can be a pretty major bottleneck. The other major bottleneck being state access, which needs to be parallelized as much as possible, which the HyperSDK is pretty much completely built around for performance. But
So we stumbled upon this, and I lost it because I was so excited by what we uncovered, I guess. So you can look for this in the next release with some additional changes related to mempool efficiency, and then after that we are pretty close to the first like Mark 1 HyperSDK DevNet. I
think what the main thing that you've been asking me for is PrecompileEVM block header removal at this point.
So that's the like if I got that, that's the icing on the cake. So great transition. So the last thing here that we have talked about before is the TX block, like in root block usage, and I still have a placeholder to deal with that in the milestones here, and that really is to get around the PrecompileEVM storage of blocks. And so what I mean by that is the PrecompileEVM, when you are running your own virtual machine here, assumes that once you give it a block, or like a block is verified and accepted, that you never want to get rid of that block, which is a reasonable assumption, right? Because if someone is full syncing the network, like if there's not a lot of people have those blocks, like they're not going to be able to full sync the network. And for some people, that's a hard requirement. So reasonably, it makes sense that it was designed that way. But if you don't want that, there's not really an option to get around that. And so if you have, like, if you're running like a really high throughput subnet that's producing, multi-megabyte blocks every couple hundred milliseconds, you're going to fill up your disk pretty quickly, and it's not going to be possible to avoid that. And so one really nice benefit that we got when playing around with the TX blocks was that I had full control over the TX block storage, and after so many blocks could just delete it. And so the holy grail of VM design, right, is that you can get to a place where like your VM is running steady state, which is it's not growing at all. It just is executing. And for a validator, like that is like the dream, and something that we got achieved with like the light VM work we were doing, but really would be great to get on any hyper VM. Because if you're running high throughput, that ends up being the problem, right? Like you can't just have like ever growing disk usage. That's, totally ruined. And so the other thing we're doing there to get around that is adding like some state rent related stuff to also control like unbounded state growth. It's really more of a state burn than a state rent. Like once you create the state, you're not getting it back but it's just an extra fee that needs to be paid to compensate for the growth of state. And as we've seen in experiments with like state cleanup, no one ever cleans up their state. So like, don't build the mechanisms to give your state rent back, because it's never, no one's ever going to get it back. They're just going to use it to abuse the fee metering on your virtual machine. But in the case of capping the headers, this is a really nice feature that's going to come to the Proposer VM, hopefully, whenever Steven decides that it's
so.
right.
So the main complexity for actually implementing that is because the Proposer VM does not assume that it is writing to the same database as the inner VM. And so there is a lot of logic around database consistency. And so it is very subtle around requirements for writing the blocks. And it is even more subtle around the requirements if you're deleting the blocks. So I've done a couple of passes that I'm not happy with, but this probably will be added as some form of subnet config where it defaults to keeping all Proposer VM headers, but ends up removing them if it's configured to do so after some like height pass tip. But yeah, it's definitely a subtle change. So definitely not part of the original thought process of the Proposer VM, but it'll be a huge unblock for these VMs. Now, one interesting thing is you probably do need to have some node in that subnet that isn't deleting these things, so that you can provide a historical archive look back to the full chain. So you will need to be pretty careful as a blockchain designer if you are playing with this. But it just unlocks such speed that it's hard not to take on that additional complexity. So
yeah, especially if we also don't even have to store the blocks in the VM as well, just have to store the last accepted block and the genesis, which the Proposer VM would also, in this case,
I mean, you can already do that technically. Like the Proposer VM was designed to be a seamless wrapper around the VM. So the VM interface specifies that you have to be able to fetch all accepted blocks. And obviously we're going to be changing that to be a little bit looser with the Proposer VM if we want to restrict this. But if you kind of break that abstraction barrier and look at what the Proposer VM is actually doing, it only ever cares about the genesis and it cares about any blocks prior to the Proposer VM activation, which, assuming it's a new chain, is just the genesis block. And it requires that the inner VM knows what its last accepted block is. And the reason it requires that last accepted block is specifically because of the database inconsistencies that can happen, where the inner VM may arbitrarily roll back due to like a database like fsync failure. And so like we have to like kind of handle that logic. And if we were able to atomically commit across those databases, we wouldn't need that logic either, and you just need the genesis. But we'll probably won't remove that because the inner VM is using a totally unrelated PebbleDB database for at least HyperSDK, and we probably wouldn't want to remove that capability. So anyways, yeah.
Yeah. It's pretty cool stuff. I'm pretty excited. All the things to get like HyperSDK off the ground. We have some other stuff we need to talk about during this dev community call, so I'm going to cut ourselves off there, at least on the HyperSDK side of it. But just know that there may be some interesting WASM repo drops soon. So we'll see. We got a lot of stuff working. Sam have a lot of stuff working internally, and it's very close to the time to make that more accessible and easier to collaborate with. So that's the last thing I'll add there. I think we should go into now the DevContainer stuff with Martin, which is super cool. Sorry for going, I think 20 minutes after about when you were supposed to come on, but
no worries.
Yeah.
Hi everyone, I'm Martin. I'm dev role at Ava Labs, and now I'm trying to get us out of this rabbit hole these guys got us into to something way more high level. Cool. So so what I'm going to talk about today is containerization of development environments, right? Like developing a new ecosystems can be very challenging. There might be some very complex development environments that need to be set up, and this can be like a barrier to entry, especially for new developers. So I'm just going to do like a quick recap of why one would customize a virtual machine and what kind of the app chain thesis is. And then we can see. So one basic thing about smart contracts is they are too incomplete, right? Like, so if I write a Solidity smart contract, I can basically do anything. And like simple operations are pretty easy, but it can get very expensive if I do more complex stuff, right? So there we can look into ways like, okay, how can we still adapt, like create these new use cases for blockchain applications by breaking out of the EVM. And that's kind of the idea of precompiles, right? So just a quick recap. So basically a precompile is the idea of I like define a Solidity interface for some function. In this case, it would be a SHA-256. But I don't implement the function itself in Solidity, but implement it in a low-level logic that might be more gas efficient, or I can use existing libraries, right, if I don't want to re-implement all kinds of stuff. So in this example here, this is like a shortened version, simplified version of it. But as you can see here, with precompiles, we have the ability to run Go code, but call it as if it was a smart contract, right? So this is like super powerful, and that's like also super unique to kind of the Avalanche ecosystem, or generally speaking, the app chain ecosystem, right? Like, so if we compare like Avalanche to like one chain fits all systems with subnets, like we have this ability to add custom functionality like precompiles. There are many other reasons why we should go for subnets, right? Like we can customize gas fees, regulatory reasons and everything. But basically these, like one major reason to go for subnets and customized VMs is definitely that we can add custom functionality, either in Subnet EVM, Precompile-EVM, or as HyperSDK. But there's a big but, right? Like there's like one major thing. It's way more complicated for developers to get started in this development of customized virtual machines, right? Like, so if I build a Solidity dApp, there's like a massive ecosystem, right? Like Hardhat, it's pretty easy to get started. I can use Remix Online, all kinds of stuff. So when I now start building a virtual machine, customizing a virtual machine, there's like a long process, right? Like, for example, like if I wanted to build something like customize a Subnet EVM or Precompile-EVM, I would have to set up my IDE, install Go, set up Go path, lots of environment variables, install Node, Avalanche Network Runner, AvalancheGo. I need to clone the repo itself and everything. So it's quite a lengthy process, and a lot can go wrong. So we, as a developer relations team, and also a massive shout out to Rodrigo, my intern there, came up with a way to simplify this and make it much easier, especially for new developers getting started. So the basic idea is kind of containerize this development, right? So we go away from having the developers set up this all on the local machine, but just providing a Docker container, basically. And they can run this, and everything they need to develop Precompile-EVM or Subnet EVM is in this Docker container, and they can just spin it up. And this, on the one hand, reduces the number of steps, but also the steps that the developers now take are a lot more difficult to mess up, right? Like, so while setting environment variables, a lot can go wrong. But like installing Docker, that's pretty straightforward. Like everyone can do that pretty much, and cloning a repo. So we have like only a few steps now, and they are much easier. And then we took this to a next level where we're like, okay, let's look even further. And people that just want to play around, maybe they don't have Docker installed, you know, they just want to like check out quickly, like how can I work with this? We came up with this tool from Microsoft GitHub, Codespaces, where we basically launch the development environment on a GitHub server, and you just connect through it, either through your browser, or you can also connect your local IDE to it. And this like really opens the doors for many developers that just want to try it out, right? Just want to check how it works. Not going to have to go through this, 1-hour process of setting up the development environment, but just like spin it up in a few minutes and get started. right? So now we can switch to the video. So I brought a little video here, and you can see pretty much what we do. So we go to the Precompile-EVM repository under the Ava Labs account. And instead of cloning the repository to our local machine, we're going to go to the code and code spaces. And there we have a button to kind of create a code space. So what you're seeing here now is in our browser, we see some terminal-like window that basically go through the steps of building this container in the cloud. I sped it up a little bit, so it takes a little bit longer if you do it on your own machine the first time. Otherwise, it will be pretty quick. But as you can see now, we are developing in the browser, right? And it does like a lot of stuff for us automatically. Avalanche Network Runner is already installed. Now it's building the Precompile-EVM initially. So lots of stuff is going on. So as you can see here now, we just use Avalanche Network Runner to spin up our own like Avalanche Network Runner server. And from there, we can pretty easily now spin up an Avalanche network with a Precompile-EVM. They're just like out of the box, so nothing customized yet. But as you can see here, like only a few minutes later, we have an Avalanche Network Runner, running on the GitHub servers. We have access to the virtual machine through an IDE. And yeah, we see already the chain is running. And now what we can even do is we can connect to that chain, even though it's not running on our local host, but on the GitHub servers with core. And just show real quick that we can do a transaction, right? And from there, obviously, you can now go customize, play around with the EVM, change some values of the Genesis block. Yeah, like pretty out of the box, like especially for new developers that may join your team or something, this might be super easy. So as you can see here, we're just sending some tokens. And this is not happening on Fuji. This is not happening on the mainnet, not on my local machine. This is happening like on a server provided by GitHub. Right. Yeah. So went through, and there we see it in the logs. And this is all happening in the browser. You could also connect through it to it. So can we switch back to the slides real quick? Cool. So
we pause there for a second before you. That's pretty cool. So yeah, I mean, I think one of the big, like, not only the ability to just like hook up a wallet like that, but you can also share that link with other people while it's running, which is so nice.
Yes.
And then also, like, a lot of people that are still getting familiar with the EVM don't have the necessarily software dependencies to run something like that, or like the familiarity with curl or like different things in their network runner. So being able to just spin that up with nothing on your computer is huge. So I think that's just want to call out why that is pretty cool. Yeah. And then I want to add it to the HyperSDK now. But
yeah, that's good. That's good to hear. That's definitely on the roadmap. And also this opens up a lot of doors for people that may not have like the required hardware requirements, right? Like you can do this basically on an Android tablet somewhere in the world with basic internet access, right? Like you don't need anything, like your device, now your development device can be super simple and doesn't have to have massive resources to, like run 5 local Avalanche nodes and all this kind of stuff. Like you can do this basically from any device that can access the internet and run a web browser or like a decently complex web app in your web browser, right? And this was definitely something we worked on for a while, and want to open this up here. There's like so this was all very, very quick, right? So I don't expect you to do this, but like just from what you just saw. But I want to encourage you, if you want to try it out, go to academy.avex.com, and there's a course a little bit down there. It's called Customized EVM. It's still in beta, but basically what I just showed you is all like very well described there, step-by-step instructions. And we definitely love to get your feedback. And in the future, we definitely want to like adapt this in more development setups and Avalanche for more virtual machines. As Patrick said, like it's a super powerful tool. We can use it like now to collaborate on this environment, right? Like multiple users could log into the same code space. We can collaborate on the same instance, maybe a PR or a certain branch, and we just play around there and don't have to sync our local machines anymore. So this is kind of like the idea what we're working on here. And super excited to hear what you guys want to hear. So I think we have some questions, or are we going to do them later?
Yeah, I mean, I see the questions here. I think we typically do those now. So I think you can see those. So I don't know if you or Gabriel want to maybe ask the question, and then Stephen and I or whoever can respond, just so it's not us reading to ourselves.
Also, don't forget to update your Brave browser. It's also so.
I was wondering if someone would call that out, but yeah. Yeah. Okay. Cool. So yeah, I hear I should ask some questions. So we have the first question: what infrastructure strengths on AVAX help Cortina 7 shorten transaction processing time? When the transactions flow reaches the peak, will there be delays or slippage?
So I also caught this is from I think Win Min 2. So sorry if we're mispronouncing that, but that is good question. So when we're talking about like delays or slippage, in this case, usually people are referring to like when the target. We've seen this before, and what will happen is the chain itself, typically the C chain is what people are referring to in this case, is that there's a gas target per 10 seconds. And as soon as you start to surpass that gas target per 10 seconds, the fee price goes up because the network or the chain is trying to constrain the usage to reach the target. Why is there a target? It is about constraining the amount of state growth that can happen, as well as constraining the amount of like processing all nodes in the network had to do per 10 seconds. Is it the perfect way to do either one of those things? That's an open conversation, particularly the state growth aspect of it. But nothing that we've added in Cortina 7 modifies the gas target at all. It just, the big changes that we added were more so to prepare for the integration of warp messaging into that, so that the gas cost that we would set for warp messaging on the EVM could be lower. Because the important thing here is not that you like arbitrarily set gas costs, right? Like if I set gas cost to 1 and the block target or like gas usage for the 10-second window is like 15 million, well, like sure, you can like submit 15 million transactions, but if the gas target is totally out of whack with how long it takes to actually compute those straight state transitions, the whole network's going to go down, right? Like, so it's really a DOS resistance mechanism at its core. So nothing we're doing changes that gas target, but it makes the gas cost, like the true gas cost of the warp messaging verification, cheaper, which is huge and critical for the success of warp messaging. We are pursuing changes to be able to increase that gas target on the EVM. And that is really the migration of the EVM to MerkleDB instead of using like the TRIE database that's included with it. By doing that, we would be able to better constrain the state growth, or like not the state growth, let me take that back, the disk growth, because we're only storing the current state in that case. That will be accompanied by a brand new archival database as well. That will also mean that like even if we increase the transaction activity on the chain, that it doesn't absolutely blow up archival nodes, which are storing everything via TRIE nodes instead of like as you'd expect with like key values, which if you're interested in this conversation, you should check out like some of the Aragon GitHub stuff, which is super interesting on this topic. So long story short, the transaction processing time is not really the constraint. It's really the how much targeted is the constraint. So
I also want to just kind of like underscore one of the things that you just said, which is that this oftentimes surprises people, which is that the majority of the state that is taken up by, like, say, AvalancheGo's disk is not actually needed to verify new blocks or even to like provide nodes to sync the network correctly. It is oftentimes kind of remnants from the hash-based Merkle tree, which is essentially storing state at historical points. So the actual blockchain node has to have this like historical state, even though it's not necessarily needed because it's computationally difficult with the current structure to remove it. So MerkleDB solves this problem. There are other works on solving this problem as well in, say, like Geth. I think Peter has been tweeting recently that they're about to merge in one of these solutions, which will be really cool for them. But yeah, I just want to like underscore that like there's a big difference between the actual disk size and the current state of the network, which oftentimes surprises people. Yeah.
Yeah, I think there's one more if you want to ask that one, Martin.
Yeah, sure. So Robbie is asking, as a Web2 developer, how do you best start finding your way in Web3, and more important, start using Avalanche blockchain for your ideas?
This is, I think, really, it's super different for everybody based on the type of learner you are. I, for one, was always like a learn by doing person. And so I think there's a lot of pressure when you're getting into Web3 to like, as you try to like use your own ideas, is that you basically couple the act of learning with creating something new. And that's like quadrupling the complexity of learning, in my opinion. What you really want to do, in my opinion, is take something off the shelf, like, hey, like I want to create a DEX, or like, hey, I want to create like something that exists and it's not well defined, but there's like 1,000 examples, and just try to replicate it and learn something without doing something new first. And then as you get more comfortable, start tweaking little things about it. This is how I learned like app development or like all this sort of stuff, the same thing, right? Like take something that exists and just start tweaking it as you start to get deeper and deeper into it, so to expand your framework, because you can't learn everything all at once and apply things that there is no guidance for as you learn. And so my recommendation is to start off with something that exists and just try to copy it, like make a clone of whatever you like to use, I guess. And then from there, get deeper into how you may change that and start to stretch your knowledge. But the work that Martin and the rest of the DevRel team are doing on the Academy is meant to really be focused on this. So if you have particular feedback on like maybe gaps or things that are confusing after working through those things that are preventing you from getting deeper into Web3, that'd be a great place to share that feedback.
Yeah, that sounds awesome. Yeah, definitely check out academy.avex.com. I want to plug it here one more time. There's that question screen for it, basically. So now I'm super excited to introduce a new Ava Labs team member and Michael to the community. And he can just talk a few sentences what he's up to.
Hey, folks. Nice to meet you. I am our new director of developer relations. I'll be working on a new project, a new initiative that we as an organization are going to be launching. Basically, the long and short of it is it's a program that will take place a couple times a year. And we will be basically figuring out a way to support developers building on chain, as well as then incentivizing you all. So this is a process that I just started a couple of weeks ago. I've just gotten to know everyone, and now really starting to build. Hoping to launch later this year and or Q1. So apologies for the vagueness, but don't want to reveal too much too soon. Hopefully come back next time for more. It's something that, not only will we be launching, but in time, we'll in fact be reaching out to a number of you to really build with you, right? Like that's the Web3 way, but certainly my way as well. Whatever I'm going to be building, I don't want it to just be in my little hermit shell, but rather with all of you as well. More to come soon. Excited to get to meet you all. I am on Telegram, so feel free to get in touch with me there. Other than that, thanks so much. Great to meet you, and looking forward to more. Back over to you guys.
Thanks, Michael. Yeah, I think Gabriel, if you want to come back on stage, we can wrap this up.
Okay, I am waiting for Kyle to bring me back. All right, thank you so much. Okay, so yeah, thank you very much, Michael. Welcome to the team. We're very happy to have you on the team. Looking forward to all your amazing work to come. This is usually when we pass around the mic and get some last-minute thoughts. So, Martin, last-minute thoughts?
Yeah, just very excited to see what's coming for the DevContainer. So very pumped to hopefully be back soon to make the HyperSDK much more accessible to the broader developer community. Yeah.
Awesome. Thank you. Steven?
Yeah, no, really, really looking forward to 110.8 coming out, especially with that subnet state improvement that we'll be playing around with. And then, yeah, I think after that, probably turning my focus to 111. So should be fun. Yeah.
Thanks, sir. And Patrick.
Just trying to get to that DevNet with the HyperSDK so it's easy to play around with. Yeah, a lot of ideas for what we're going to do when we get to that point. But I think that, yeah, that with this like really light P chain plus the HyperSDK plus like the header pruning, like it should be pretty close to where we want to be. And then you add programs on top of that, it's going to be pretty cool. So yeah, just working on that.
Excellent. All right. Thank you. So thank you, everybody, for joining us. We will be back in 2 weeks. We already have 2 guests lined up for that, so that should be very exciting. As I mentioned, my name is Gabriel Cardona. You can follow me on Twitter or X at CG Cardona. That's CGCARDONA. Also, please check out the Avalanche Developers. That's one word, Avalanche Developers account if you want to stay up to date on everything that's happening. And also check out academy.avalanche.com. I know there was that question from Robbie about how to on-ramp into the ecosystem as a Web 2 developer. That's it. The work that Martin and the rest of the DevRel squad have done is really, really awesome, and that is going to grow into an amazing resource. So go check it out now. And that's it. So thanks, everybody. We'll be back in 2 weeks. Thank you so much. Cheers.